Hello and welcome to this presentation. This presentation describes the ICASSP 2026 poster, Improving Numerical Stability of Normalized Mutual Information Estimator on High Dimensions, authored by Marko Tuononen and Ville Hautamäki from Nokia and the University of Eastern Finland respectively. The key contribution of this work is a log domain reformulation that prevents numerical overflow in high-dimensional KSG-based normalized mutual information estimation. Let us begin with the motivation. Mutual information, often abbreviated as MI, is a widely used measure of statistical dependence between random variables. In simple terms, it tells us how much knowing one variable reduces uncertainty about another variable. This makes mutual information useful in many areas of signal processing, machine learning, feature selection, and scientific data analysis. However, for continuous variables, mutual information is usually not available in closed form. Therefore, it must be estimated from data. Another challenge is that mutual information is unbounded and scale-dependent. This means that raw mutual information values are not always directly comparable across datasets, dimensions, or different experimental settings. To address this, normalized mutual information, or NMI, is often used. Normalized mutual information provides a bounded dependency measure, typically between 0 and 1. A value close to 0 indicates weak or no dependence, while a value close to 1 indicates strong dependence. This makes normalized mutual information attractive in applications such as molecular dynamics and interpretable machine learning, where comparable dependency measures are needed. In this poster, we focus on a KSG-based estimator for normalized mutual information. KSG refers to the Kraskov, Stugbauer, and Grasberger estimator, which is a popular k-nearest neighbor-based method for estimating mutual information from continuous data. The specific problem addressed here is numerical overflow in high dimensions. In the KSG-based NMI estimator, scaling-invariant k-nearest neighbor radii are used to estimate local data densities. These radii are normalized by a factor that depends on the sample mean of the raw k-nearest neighbor radii raised to the power of the joint dimensionality. Mathematically, this normalization factor involves terms of the form epsilon raised to the power dx plus dy, where epsilon denotes the raw k-nearest neighbor radius, and dx and dy are the dimensionalities of the two marginal spaces. This computation is manageable in low dimensions, but as the dimensionality increases, raising the radii to a large power can become numerically unstable. Even moderate radius values can produce extremely large intermediate values. Eventually, this can exceed the floating point range of standard numerical computation, causing overflow. When this happens, the estimator may fail, even though the underlying mathematical expression is well defined. The proposed fix is to move the problematic computation into the logarithmic domain. Instead of computing the normalization factor directly, we compute its logarithm. This allows us to avoid forming very large intermediate values. The key idea is to apply the Log-Sum-Exp trick, which is a standard numerical technique for stabilizing sums of exponentials or large powers. In this formulation, we first identify the largest k-nearest neighbor radius, denoted epsilon max. Then we rewrite the normalization factor so that all radii are divided by this largest radius. This is important because every ratio, epsilon I divided by epsilon max, is less than or equal to 1. Therefore, when these ratios are raised to a high power, they do not overflow. Instead, they remain bounded. The resulting expression for the logarithm of the normalization factor is numerically stable, even in high dimensions. The estimator can then use this log domain quantity when computing the normalized radii and the entropy estimates. An additional observation is that, in high dimensions, the normalization factor becomes dominated by the largest radius. In the limit, as the total dimensionality increases, the normalization factor approaches epsilon max. This behavior is illustrated in the poster's central figure. Next, let us briefly look at the experimental setup. The experiments use synthetic data from two distributions. The first is a multivariate Gaussian distribution with component-wise correlation RHO. The dimensionality ranges from 1 up to 512 dimensions, and ρ varies between 0 and 1. The second is a multivariate student's t-distribution with identity dispersion and degrees of freedom nu. For this distribution, the dimensionality ranges from 1 to 32, and nu varies between 0.125 and 10. For each case, 10,000 samples are used, and the estimates are repeated 10 times. The evaluation considers the estimated normalized mutual information, the mean and variance across repetitions, comparison with theoretical value, and numerical stability. The experimental results show that the proposed log domain fix prevents numerical overflow while preserving estimator accuracy and computational complexity. In particular, the Gaussian experiments demonstrate stable operation up to 512 dimensions. This is the main practical benefit of the proposed reformulation. It allows the existing KSG-based NMI estimator to be used in high-dimensional settings where the original implementation may fail due to numerical overflow. Importantly, the proposed change does not alter the estimator conceptually. It is a numerically stable reformulation of the same normalization factor. Therefore, the estimator's behavior and complexity are preserved, while its usable dimensional range is improved. The poster also outlines future work. One direction is to evaluate the method on real-world, high-dimensional datasets. This is important because synthetic experiments provide controlled validation, but practical applications often involve more complex data structures, noise, and dependencies. Another future direction is to explore neural estimators, such as mine, for direct normalized mutual information estimation. This may be especially relevant for interpretable machine learning, where robust dependency estimation in high-dimensional feature spaces can be valuable. To summarize, this work identifies a numerical overflow issue in high-dimensional KSG-based normalized mutual information estimation. The issue arises from computing powers of k nearest neighbor radii in high dimensions. The proposed solution is a log domain reformulation based on the Log-Sum-Exp trick. This prevents overflow, preserves accuracy and computational complexity, and enables stable estimation up to 512 dimensions in the presented experiments. Thank you for your attention. If you have questions or comments, please leave a comment below the video or contact the authors using the information shown on this poster.